Hello everyone, I would like to present our works entitled Energy-Aware Linear Quadratic Gaussians, also known as LQG, on Wireless Network Control System, shortened by WNCS, in this occasion of the 5th International Conference on Operation Research 2020. My name is Zuhair and my co-authors, they are Mr. Subhan and Ms. Tahiyatul Asfihani. We are from Institut Teknologi 10 November, Surabaya. First, let's start with our motivations of this study. Compared to the conventional control system, wireless network control system have a lossy channel wireless, which means there is a possibility that the data from the plant that being transferred to the controller is not successfully received. So a closed system will be an open loop. Consequently, the estimator will not receive the quantified signal and fails to estimate the sensor reading. Therefore, the controller fails to generate the optimal input signal that lead to the destabilizations of the system itself. And we know that the most of the device is attached with the battery that require energy. Therefore, there are a shortage amount of energy that can be used. So the scheme that can harvest the energy while maintaining control performance is needed. So we move on to the existing works. First, the SEN in 2018 studied the fundamental limitations in control design and performance of LTI, which is the grand scheme of our study. In the next few years, in 2019 and 3 years before, in 2016, Beijing, they investigated the stability analysis based on SNR only as the constraints of the optimizations of the stabilizations of the system without doing anything else. And at last, Soleimani, 2018, they examined the LQG controlled via wireless sensor network with minimal transmission power. So our main idea here, we would like to propose minimizing energy on WNCS of fading channels or lossy channels in which utilize the energy as the constraints in the optimization problem. In order to determine the reliability, we use the finite block length to achieve the upper bound of packet error rate. So we move to the system model. As you can see here from our diagram, it looks like a conventional control system, but we have a lossy wireless channel. It means that there is a chance data from the plant is not transferred successfully to the controller that possibly make a problem. As the main framework, we would like to combine of Kalman filter to find the optimal estimator and LQR to obtain the optimal control input. We move back to our diagram here. After we quantize the sensor reading from the plant, we decoded it and transmitted through the lossy wireless channel. and the remain code word is as the input of estimator. We use the Kalman filter, and the estimate data will be the input of LQR. Then through this we can generate the optimal feedback. Power scheduler play the main role here, since if you have a bad channel, it can produce the bad data. What I mean with bad here is we have less chance to transmit our data that can generate stability. This is the system of WNCS. It's like a normal system, but the things that should be interesting here is the Z. The Z is the quantized data with the NK as the quantized noise. Okay, we move to the communications channel model. We introduce gamma. Gamma as an indicator if data is successfully being transmitted or not. Gamma K will be equals to 1 if the HK or the decoded sensor reading is transmitted successfully, or 0 if it's not successfully transmitted. Okay, we denote the signal to noise ratio as rho K with the ESK or energy per symbol over the N0, which is the noise spectral density. So we implement the block length approximations, the block length approach. We determine the packet error rate as these equations, with N is the length of block or the length of HK in our previous diagram, and is the length of HK, and beta as the Rayleigh distributions. And the packet success rate, we determine it as these equations. Next, for the simplicity, we would like to express the energy per symbol as the functions of packet success rate. So we make these functions which the PSR as the argument of energy per symbol functions. We write the ESK equals to the C PSRK that defined in the domain S. Okay, we assume that the controller and power scheduler can store a memory. This is what a controller can store, and this is what the power scheduler can store. And this is the cost functions of the control performance. Okay, we construct the Lagrangian functions with the constraints is the control performance cost functions to minimize the energy or the functions of PSR. So we will get the optimal PSR and U that keep the stability of the dynamic of the system. So we move on to the proposed scheme. For figure 1 here, it looks like a normal Kalman filter, but the only difference here, there is a chance that the data cannot be received by the controller from the plant. So there is gamma here. and here. The proof of this theorem can you see in our paper. This is the optimal estimate state at power scheduler, and to ease our constructions of optimal input policy, we define the value functions as you can see here. This is how we try to optimize the input function, the input policy. Okay, we got the optimal input. We use the LQR with the popular Riccati equations, and we define the cost functions C with the arguments of PSR and optimal control input used there, which independent to the system and the system estimations. Okay, next we get the optimal packet success rate here. We do some algebraic and mathematical statistic operations to get this, and we come to the analysis and discussions of this study. Okay, we use a fundamental benchmark in control theory and robotics, which is a wheeled inverted pendulum, because it is simple and its stability can represent the necessity of control in network control system. Okay, this is the mechanical characteristic of wheeled inverted pendulum that we use in these simulations, and this is the motion system of wheeled inverted pendulum. Okay, we can see the result of simulations here. It's clear that all the states of wheeled inverted pendulum reach their stability on their reference point. This is the first state of wheeled inverted pendulum, which is horizontal positions. This is velocity, angles of the pendulum, or the deviation angles, and this is the angular velocity of the pendulum. And from the graph here, we can see that the system, the transmitter, tried to turn off, which means the energy saving procedure that we have constructed before in theorem 1, 2, 3, and 4 is works here. And the control input is not changed too much, which means the system is stable. And the conclusion and future directions of our study. This study successfully combines LQR and Kalman filter that use minimal energy usage on wireless network control system while maintaining the stability of the system. The dynamic system reach stability with the minimum usage of energy. And for our future directions, there is a possibility to do a research on communication channel with the memory, or implement our procedure in multiple practical systems. Okay, I think that's all. Thank you very much.